Hello everyone, my name is Shano. Today I'm presenting you my deep learning project, Smart Power Forecasting Electricity Demand using LSTM and TFS model. So let's get started. Okay, so the objective of our project is to understand data provenance and quality, also explore the key demand pattern of the data, benchmark classical versus deep learning baseline, and present a best performing model and the next step. Okay, so let's start with the introduction of our project. So the electricity forecasting is critical for grid reliability and planning. So the load have to be balanced. The generator create the load and the consumption have to be equal. So that it keep the system grid stable operation. So the problem short-term load forecasting for smart grid operation is critical. So we will do the deep cleaning to see that. So let's move on to the data collection and pre-processing. So we use the data set of 370 smart meter in Portugal, recorded at 15 minutes interval from 2011 to 2014. We drop meter with over 90% missing data. So it's around 16% of the meter. So data is aggregated and reprocessed by filling any remain missing value, and this prepare for the input into the deep learning model like LSTM and TFT. So we can see the plot on the top is the daily average total power consumption from 2011 and 2014. It's so clear annual seasonality with the peak in the summer between maybe May to October. It maybe due to the high usage of the AC, and it going down maybe from November until May. So it in the winter time. So sometimes it going down. It reflecting maybe due to the weather condition, and we see a big jump at beginning of 2012. So we will see what happened there. And the second plot on the bottom is the 15 minutes total load for 1 week from January 1st to January 8th of 2012. It shows a clear daily circle are visible up during the day and low at night. Cool. Okay, so from that we start doing the EDA. Then we look into we jump in the 1 year at 15 minutes resolution. We can see a yearly peak in summer, June and August. The winter occur around December to February. This suggests our model should capture yearly cycle, either via seasonal feature or by the TFT attention. And jumping into 2013 at 15 minutes resolution, so the classic daily double peak, morning and evening, and flash weekend and holiday. Now we can see clearly yearly peak in summer and also the winter going down. This is the trend. We can see it increase from 2011 to 2013. It maybe due to more meter happened at beginning of 2012, and then stabilize from 2013 to 2014. And the line top around 150 kilowatts daily average. We also check the lag structure for our forecasting model. We analyze the autocorrelation function AFC and partial autocorrelation function PACF for the daily average total loads. So this analysis help identify how strongly past observation influence the future one, and guide the selection of input window size for the model like LSTM and TFT. So the ACF remain extremely high, near 1, confirming a non-stationary series with very strong persistence. The PACF show a huge spike at at beginning near 1 here. After that, more spatial correlation die out near 0. So the implication for our feature in a model that we need to give our model access to at least the last 24 hours. That means we have 15 minutes with one data, so we need around 96 data point per day to capture the daily peak, and ideally also the last 7 days or 672 steps for weekly cycle. Okay, so with the EDA we finished. Now we're moving to the modeling. Then we start with baseline. First with Naïve model. The Naïve model we do the trend test splits for the last 30 days, around almost 3,000 points. So with Naïve forecast, it also known as a persistent model, assume that the prediction value at the time t will be the same as the actual value at t minus 1. This model is simple, but it's very effective for short-term forecasting in stationary time series. This serves as our baseline model to compare more complex approach like ARIMA, LSTM, and TFT. This requires no training. We compute the prediction on the test set, then measure the mean absolute error, MAE, and the root mean square error. We have the calculation out here at 3,441 for MAE and 5,167 for RMSE. So we will use these two numbers as a baseline to compare with other model to see any improvement. The next baseline we're going to look at a ARIMA model. This model to the daily average total loss. ARIMA is useful for capturing a linear trend and auto-aggressive dependency. The selection it will be 510. The 5 is auto-aggressive regressive lag. The D is the first order difference to enforce stationary, and we use no moving average. That means Q equals 0. So the model will train on the daily average series over the training periods from January 2011 to December 2014, then used to forecast the final 30 days. So the ARIMA result with MAE around 33,000 kilowatts and RSME around 35,000 kilowatts. Compare with Naïve result, it's performing significantly worse. So that means the ARIMA model on daily average data is not sufficient here. We might need to either fit directly at 15 minutes frequency or move to more models that can learn multiple time scale. The third model we look at will be a deep learning model after the baseline from Naïve and ARIMA model. So the LSTM long short-term memory model will take a fixed length window of past observation and covariate from the previous 96 steps, like 24 hours, and output a single value of 15 minutes ahead forecast. So that means the 96 point of the last value will project out one value of 15 minutes ahead. So the result is a little better than Naïve model, 3,200 kilowatts compared to 3,400 for the MAE, and RMSE 4,500 kilowatts compared to 5,100 kilowatts. So it slightly outperform the persistent model. So next we will move to the second deep learning model, TFT, Temporal Fusion Transformer. This is the powerful deep learning architecture for multivariate time series forecast. It combines the LSTM model based sequence modeling, and then it adds the attention over time and feature. Also, it adds the gate mechanics into that. So to provide the interpretable attention map. So the TFT result come out the MAE equal 2,774 kilowatts versus the Naïve 3,400, and RMSE also significantly lower at 4,100 kilowatts versus 5,100 kilowatts. Then we also have the plots on the bottom, the 2-day plots, so that the model capture both load trend and daily cycle quite well. So here the model performance summary, and then we see that the TFT have the smallest maximum mean absolute error and root mean square error. The LSTM and Naïve following, and the worst will be ARIMA. So we also check the error distribution. We plot the residual distribution for each model to access the bias and variance. So from 4 plot right here, we see that the TFT histogram achieve the best average accuracy, and also the most stable and unbiased error distribution. It very spy up at 0. Here also we're looking further to the TFT model. We examine the MAE by weekday and weekend. So the weekday showing a little better than the weekend, likely due to a more consistent daily pattern in electricity demand from business and infrastructure usage during the weekday. And the weekend is less predictable, still show strong model generates with only different 100 kilowatts increase. So the plots on the right showing the MAE across 24 hours. We can see the lowest error occur between midnight and 7 a.m. When the loss pattern are the most stable, and then it have a sharp increase around 8 to 9 a.m. And slowly stabilize, going down up until 10 at night, and it is significant going down. So from here we can see that TFT the most stable and unbiased error distribution. So the conclusion and the future work, the TFT outperform LSTM and other baseline model for the short-term forecast. So for the accurate interpretable forecast, the TFT ready for the real-world deployment. The future direction will be include adding more data like weather inputs to see why the load change, also maybe due to the holiday, and then we do the forecasting multiple step and model assembling. So that's the end of my presentation. Thank you for your attention. Bye bye.